That, as I know, a lot of people come from the US. I see people from Europe, people from Israel, from people from India and different other places. So I'm really, really happy that you guys are joining us today for how advanced quantum algorithms are built, tested, and benchmarked, a use case powered by Wiser and Classic. So maybe just a little bit about Wiser before we get into the use case. Just a little shout out first to the co-founders of Wiser, Prachi and Vardhan. It's like many people don't know this, but Wiser, although by that we go by that name recently, it's been almost a decade in the making. So Wiser is a science, like it had another name previously. So Wiser is a science education and research organization which accelerates the transition of frontier science into real-world capabilities. In the last almost full decade now, the team has trained over 73,000 scholars from different parts of the world, so from 120 countries. We've done 19 projects with 9 different partners in completely multiple different sectors. From finance to energy and many others. We have 46 active quantum research fellows at this moment in time, and we have 85 plus quantum providers and strategic partners that we've built over the years. So the verticals that we actually are part of, one of them is our quantum ecosystem, which is very, very strong. Now we're in the Colorado ecosystem, and we've built a very good ecosystem in India as well. We have self-paced learning from basics to executive programs, so 101s to executive programs. We have our research arm, which I'm one of the people in charge of, where we do custom R&D expert projects with all IP retention to our partners. We have our flagship summer program that's coming up at the end of June. So I would encourage you all to go on our website and have a look at that. And we have something for startups called the Insider Program to give more visibility to the different startups in quantum and AI, such as Quantum Soft. So first, I will just one more thing. If you have your phones, you can scan these QR codes. So one of them is about the top quantum algorithm papers of winter 2026, and the other one is the actual paper. So I will just get into first introducing our first speaker, which is Ron Cohen, fault tolerance team lead at Classic. So with a Master's of Science in Electrical and Electronics Engineering from Tel Aviv University, and a Bachelor of Science in Computer Engineering from the Hebrew University of Jerusalem. Ron has extensive experience in hardware design, signal progressive, and navigation algorithms. So Ron will get into this as our first speaker. And then our two other speakers are Viraj, a quantum computing researcher at BQP. Viraj is a quantum computing researcher working on quantum algorithms and their applications. His research focuses on block encoding techniques, variation quantum methods, and quantum linear solvers, with applications in areas such as computational fluid dynamics, simulations, and physical systems. And Dimitrios Granas, who is a postdoctoral researcher at the University Carlos III of Madrid, and he works on lies at intersection of quantum science and theoretical physics. I will now leave the room for Ron.
Thank you so much, David, and thank you for arranging this amazing webinar. And I'm excited to be here, and it's great to meet you all, guys. So let me just share my screen. A moment, let's see for the full slideshow. So can you see my screen well now?
Yes.
Okay, great. So just about Classic. Who are we? What are we doing? And what is the connection here to Viraj? So I'm proud to work in Classic for more than 3 years. At the beginning of my journey as a quantum software engineer, when I also worked with Viraj on his amazing, not the one that he's presenting, but another amazing project he's done on finance using the Classic platform, and later on till today working in BQP, doing really amazing job. And I'm following Viraj and expecting to see your great research. So who are we, Classic? We are a quantum software company. We are building software that help developers to build their algorithms, their applications, funded after round C, $200 million. Our main development R&D site is in Israel, but we are also located in the US, Europe, Japan, and Korea. Proud to be invested by big companies you all know, like IonQ, AMD, SoftBank. So the classic platform, which I will show you just now, and at the end of the day, a hardware-agnostic quantum software platform that allows governments, enterprises, national organizations to develop AI, to develop quantum AI at scale. So just to show you what is the platform and what is it made of, so you understand why it becomes easy to develop with the platform. The platform is composed of a high-level language that allows, just as there is a clear difference between assembly and Python when you're programming to a classical language. So this is the same thing, a language that we developed that allows building algorithms at scale. This language is leaning on a compiler that is automatically optimizing whatever you code for the hardware that you choose. So you don't need to change your model. This is agnostic. You write once and you compile and optimize to whatever quantum computers that becomes better. You can benchmark and compare, but the compiler is treating this for you. You don't have to change your high-level intent because the language is focused on the intent and not on the how at the gate level this is implemented. Visualization, which I will show you to debug very efficiently and to see very well what the program is doing. Execution, which means running on a simulator or on different hardwares, again, without changing the model, just easily choose where you want to execute and easily understand the results. Library with hundreds of algorithms and applications, which all of them are maintained to the latest version of Classic. Nothing is broken, no open source that you need to understand how to make it working. Everything is maintained. This huge library is thanks to the fact that we have a high-level language that allows both our library team and our users to donate into this library and to enrich it and make it bigger and bigger every week. And based on so many examples, we have the AI code agent that at the end of the day allows you very easy, thanks to the high-level language and the library, to build whatever you like. You can upload an article, tell him, build it for me, or you can discuss with him. He is your quantum engineer. If you have a team that need the quantum engineer, he's your guy. So as we said earlier, for all different kind of users, including both experts or industry experts, which means you don't know quantum, but you are expert in chemistry or CFD or whatever, but you need a quantum agent, or for software engineers, allowing not just the easiness of coding, but also scalability. Because if you want to code at scale, if you want to make big application, let's say it's grossly impractical to do it low level, and becomes actually possible with a high-level language and a compiler at scale. So who is using it, whether it's students or enterprises like BQP here, for example, which Viraj is working there, Microsoft, Citibank, HSBC, Rolls-Royce, for different kinds of use cases, whether they are finance or chemistry or quantum machining, for all different kinds. This is a product that allows you to code faster. And so let's see very shortly what is it, and I will leave the stage to Viraj. You can see my screen, right? The entire screen, just making sure. What does a high-level language mean? So let's see a very simple example. Here, what I show you in the IDE, great for demonstration and trying and training. Everything is also available through a Python package. So this is QMod in the non-Pythonic version of it. So here is a function taking two quantum numbers. What is a quantum number? If there is a quantum bit, why not having a quantum number? It's composed of two qubits, and they can be also negative. So 2 means signed quantum number. It can be positive and negative, and they can have a fraction also. So two quantum numbers are prepared in a superposition, 50-50 in two different states. And the summation is a third quantum number entangled with adding A plus B? What is making A plus B between two different quantum numbers? Behind the scenes, there are many gates, and we choose the best implementations based on the hardware that we choose. But at the end of the day, the user just want to take A plus B and do it into summation. And they also want to choose which hardware to optimize. Do I want to minimize the number of qubits? Do I want to optimize the depths? Do I want to optimize for a hardware that is Alice and Bob, or do I want to optimize for IBM, for example? So once I choose something, I don't need to touch the model. I just optimize for this specific hardware. So I get a visualization of my program. Different programs, for example, if I want to optimize depths, I can just with paying 10 qubits, so the depth is 25, but if I can compromise on this and make a 35 depths, I can save 2 qubits. If my hardware is only 8 qubits, so by paying a little depths, you can get the same A plus B, and the compiler is taking care of it without changing the model. And if you want to debug and ask yourself, okay, I need to prepare A, I see it as a block, but maybe I want to see how do I prepare A, so I can go inside and see the gate level. And the same for what is adding A plus B. And of course, I would see different implementations or different hardwares. And if this is fault tolerant, where I need to decompose to T gates, for example, so I see that everything is decomposed into T gates and so on. So this is about visualization. And regarding execution, once I want to execute a specific program, I can execute it, whether it's on a simulator or NVIDIA simulator with more qubits, 30 qubits. I can choose to run on IBM hardware, on the cloud, or Azure cloud, or any other cloud we are integrated with. And at the high level, to see that the summation of A minus 1, B1, is always matched and entangled to the summation of 0, which is very useful for matrix inversion, block encoding, for finance, for optimization. And here, for example, 0 plus half is equal half, and so on. I don't need to make interpretation of bits at the low level because I don't care about like in a classical computer. Everything else, additionally to this, let's call it the basic usage. So as I said, there is the library. So for example, if we think about chemistry, as Viraj is about to show you, so you can pick a notebook from the library and say, okay, let's here, for example, chemistry of the applications that Google developed and fully working with the latest version. Or you can also access it through the classic studio. You don't need to install Python. You also have the AI code agent inside. It already knows the example, and you can tell him, please, and you can also upload like a PDF, for example, invent new option pricing algorithm, like, let's see if it's on them, see the files, like option, whatever. I don't know. It will take maybe a bit of time, but you can see the notebooks and run AI through here. So this is the idea, and this is very roughly the platform and what we are doing. I will finish with a demonstration for this AI very shortly. And here, for example, we took an article, uploaded it to the studio, and I think it's took like 15 minutes. So we get a full notebook and another 3 hours to something that is actually working well. That's it. If there is time for questions, so I'm open. If not, feel free to approach me.
Thank you, Ron. There's one question. Apart from algorithms and applications, also offering any services related to post-quantum cryptography?
The answer is yes. This is something that we are doing in the last few months. I'm not the one who is doing it, so I don't know to give details, but if it's something that is relevant to anyone here, please feel free to approach me directly. I will write my email right now in the chat to everyone, and I will refer you to whoever is working on it in the Classic.
Perfect. Thank you, Ron. So now our next speakers are Viraj and then Dimitrios after talking about our use case. Viraj.
So I hope my slides are up.
Yes.
Yeah. Thank you, David, for your kind introduction and for organizing this, and also Ron for introducing the Classic platform very nicely. And that's the platform that we use to implement this algorithm that I'm going to discuss today. So I'm very excited to speak with all of you today, and please feel free to ask any questions you have. So this is what I'm going to talk about. So I'm going to talk about what the real world problem is why do you need quantum, what the quantum algorithm was that was proposed earlier in 2023 by the Google team, and what our main contributions were, and some of the results and insights that we saw. And then Dimitrios would take up the applications of this algorithm on some real world physical systems. And I also see Veronica on the call, so who is one of the co-authors of this paper. So we all three are very happy to take all of your questions. So yeah, let's get into the main real world problem. So many physical systems in real world can be modeled by a system of coupled harmonic oscillators. And I think there is a joke among physicists that everything in physics you can model by coupled by a system of harmonic oscillators if you're brave enough. And at least I'm not sure for how much of that is true, but at least for simple systems like atomic vibrations in a crystal, or electrical circuits, or maybe molecular vibrations, all of this you can model by a system of harmonic oscillators that are connected to each other. And for people who are new to this model, so a system of harmonic oscillator is just a mass connected to a spring. And the model is such that if you try to pull the mass a little bit, the spring will try to bring the mass back to its initial position. And the force with which the spring tries to bring the mass back is proportional to the square of how much the mass is displaced. So this is the model that we are interested in looking at. And this is one specific example of four masses connected by springs linearly, and all of these masses connected to a fixed or a stationary wall. So yeah, so this is one of the example that I've shown here, but you can have, based on whatever physical system you consider, any number of masses, any number of springs connected to these masses, and any number of masses connected to the walls and so on. So how does this system look mathematically? So I'll briefly explain you this, not going into a lot of details. Suppose you have n masses coupled by springs. So you can write the Newton's equations of motion for this entire system, which is a matrix equation you can see here. Here is the matrix which has all masses of all the springs. So it's a diagonal matrix which has masses along the diagonal. So it's an n by n matrix because you have n masses. And then you have x double dot of t, which is the acceleration of each of these masses. So it's a vector with n rows. And then you have the matrix F, which contains information about the spring constants, and then you have the x of t, which is the position of each of these masses. And here I just briefly explained how to construct this F matrix. So you can construct the diagonal part like this and the non-diagonal part like this. The problem here is given the initial condition, because it's a second order differential equation, so you need two initial conditions to solve this uniquely. So given x of 0 and x dot of 0, your goal is to find x of t. And you have a lot of classical methods to solve this problem. One method is the method of normal modes, where you can just go to another coordinate system where this system of coupled oscillators become uncoupled, and you solve the problem there, which is much easier to do through the through eigenvalue methods, and then you come back to the original coordinate system. But any method of that sort is having this exponential time complexity for solving this kind of coupled system of equations. And in this 2023 paper by Ryan Babush and others from Google, this is the question they asked: can you find a polynomial time quantum algorithm to solve for this system of coupled oscillators? And the key idea here is to map this classical dynamics, what you have given by the Newton's equation, to a quantum dynamics which is governed by the Schrodinger's equation. And this is a brief explanation of what quantum dynamics is. So in quantum dynamics, you will have an initial normalized quantum state, here given as psi of 0, and you will have an Hermitian operator called H, which is also called Hamiltonian, and you use this Hamiltonian to evolve the quantum state forward in time. And this problem is a very general problem in quantum physics. And you have a lot of techniques to find psi of t in this problem. So now our goal is, starting from this Newton's laws, can we mathematically transform this problem to quantum dynamics and then use an efficient quantum algorithm to solve it? So very quickly going through the mapping part of how to take a classical system and map it to quantum dynamics. And for more details, please refer to this 2023 paper. So this is your classical system, what you have. So you try to change variables. You define a new variable y of t, which is defined in terms of x of t, as you can see here. And you can see that y of t follows this second order differential equation. And the solution to this second order differential equation follows this equation that is given here. And you can note from the previous slide that this kind of looks like the Schrodinger's time evolution or the quantum time evolution. You can just call this as psi of t. You can call this psi of 0, and you can call the Hamiltonian as a square root of t. So you already have a quantum-like dynamics here. So we can straight away go and solve this using quantum algorithms. But the paper suggests that it's kind of difficult to have access to this square root of a Hamiltonian. So what they do is they try to take this square root of a and embed it into a larger Hamiltonian. So mathematically, we are not changing anything, but we are just solving a much bigger system because it's more efficient to do it. So this is the new Hamiltonian that is defined in terms of A. And now if you see the equation here on the extreme left, you again have the Schrodinger's equation or the Schrodinger's time evolution. With on the left hand side, you have your psi of t. On the right hand side, you have your psi of 0, and you have your Hamiltonian, the evolution term here, which is defined here. And now what we have is we have started from a classical problem, and now we ended up with a quantum problem. So all we have to do is we have to solve the quantum problem using quantum algorithms and get back to x of t's and x dot of t, which is a classical solution.
So Viraj, there's a few questions. I'll just
Sure.
one of them. From your benchmarking experience with Classic, what is currently the biggest limitation preventing these algorithms from scaling to industrial size problems?
Yeah, that's a good question. I am coming to the implementation part very soon. But yeah, so Classic is a very nice platform where you, as Ron also nicely explained, that whatever algorithmic intent you have, you know the math, you just have to write in terms of high level languages to implement that. But I can speak only in terms of this algorithm, what we are implementing. This is a fairly complicated algorithm because it needs a fault-tolerant quantum computer to actually give exponential speedups or even run this algorithm. So the time to synthesize these quantum circuits are usually very large. So it's not true for all the platforms out there, I guess. So that's one challenge. To synthesize this quantum circuits, it takes time, but I'm not sure if this is a Classic specific challenge or challenges across the software providers. But yeah, this is one small challenge that I observed at least while implementing this.
Great. We can move on.
Yeah. So I just explained how you now have a quantum problem. So this can be formalized. So this is directly taken from the paper where they have neatly formalized this quantum problem. So the goal here is to find psi of t, which is given like this. So you can see that it's exactly same as this if you plug back the definition of what y of t and b is. But only thing that you can see extra here is this 1 over root 2e factor, which is essential because your psi of t should be normalized. So this is the normalization factor. So the goal is to find this psi of t, and this paper gives a quantum algorithm to find this psi of t. So this is the theorem of the paper that talks about the efficient quantum algorithm. So proof I have skipped for now, but the paper has a detailed proof of this. And you can see here, and I would like to point your attention towards this important assumption that the paper makes, is that you need to have oracle access for K and M matrices. So for people who are not aware of this, so oracles are basically black box quantum circuits which you can use to get the entries of K and M through quantum circuits, right? So you don't have to read the full K and M matrices. And if you do that, you might lose quantum advantage. So you have to construct efficient oracles. And if you do that, then you can see that you require only these many gates to solve this problem, or in other words, find psi of t. And you can see that here, the number of gate is given in terms of log of n, log of capital N, and log of capital N is nothing but, if you plug in n is to power small n, so it's nothing but polynomial in n. So this is the exponential speed up that the paper talks about. And once you have psi of t, you usually don't read out the full quantum state because you might lose quantum advantage there as well, because the tomography kind of techniques are very expensive. So what you do is you try to measure some useful observables like energies or a subset of energies and all those things, which Dimitrios would discuss about. Yeah. So
there was also another question. How do you resolve the mapping issues during the simulation of coupled harmonics oscillators?
Sorry, can you repeat that?
How do you resolve the mapping issues during the simulation of coupled harmonic oscillator?
I'm not sure I understand what resolving means, so I have just explained what the mapping looks like. Maybe you're talking about the specific implementation, which I'll discuss soon.
Okay, great.
Yeah. Yeah, so this is a key gap that we identified when we tried to implement this algorithm on classic platform. Suppose we want to have an exponential advantage, we need an explicit quantum circuit that builds this algorithm for us, right? So, and that requires efficient oracles. So how do you build these efficient oracles? So this is something that we tried to ask in this work. And for this, we considered only a system of linearly connected harmonic oscillators and build three different kinds of implementations on classic platform. So the first implementation is kind of straightforward. We use a sparse state preparation approach, which is basically a state preparation for the initial state psi of 0, and then use a Trotterization technique to implement e to the power minus iht. So if you remember, psi of t is nothing but e power minus iht into psi of 0. So these are the two main components that we require, the e power minus iht part and psi of 0 part. So first method is quite straightforward. And the second method is what the paper describes. So they use this oracle calls to K and M matrices, and then they prepare this initial state and the Hamiltonian evolution. So we also do that in our implementation. And the third approach is kind of a mix of this first two approach, which uses the sparse state preparation of the first approach with the Hamiltonian simulation using oracles in the second approach. So we kind of mix that and give an end-to-end implementation. So yeah, we also performed some empirical resource analysis to see what the resources are and if it's within the bounds that is described in the paper, and also some physical applications that we'll discuss soon. So the first approach, in the first approach, we just have to prepare this psi of 0 and the Hamiltonian H. The way we do this is we can classically prepare the amplitudes of psi of 0 and classically construct this matrix H. And then what we do is we evolve this initial state psi of 0 using this Hamiltonian H using Trotterization. So one important input for Trotterization is you need to decompose this Hamiltonian as a linear combination of unitaries, which again the classic platform does it for us. And then you can decide what order of Trotterization you're going to use to find psi of t. And it matters if you have higher the order, lower the error in psi of t. So we choose a second order for our work, which kind of seemed to be enough, as you can see soon in the results. Yeah, so here you can see the kinetic energy that we observed for a two oscillator system when we implemented using the first approach. Not speaking too much about the plot on the left, or the reason I put this is I just wanted to show that the initial state preparation that we used, which is the sparse state preparation approach, is kind of upper bounded by one quantity. You can see here the red line, right? So, and this red line comes from the bound in the paper. So what we are trying to say from this plot is that our initial state preparation approach is kind of efficient. It doesn't rapidly increase as you increase the system size. It kind of tries to stabilize after some value of n, as we can see in this plot. So this is the first approach, first implementation. And for the second implementation, we use the exact implementation of the paper, but it required us to construct this OS and OK oracles. Just briefly talking about these oracles, right? So what does OS do? So OS is the first oracle that acts. So OS kind of picks the positions in the matrix, in the K and M matrix, where there is a non-zero value. So you're not interested in all the values in the matrix. Only where there is a non-zero value, you pick that index, row or the column index, and then OK will, the OK oracle will kind of take the value what is in that non-zero index and then load it into a quantum state. So for example, you can see these explicit quantum circuits that I have shown here for OS and OK. So for OS only here, and this is only for a linearly connected harmonic oscillator, coupled harmonic oscillator. And now once we have this, we can prepare psi of 0 and then use QSVT to evolve this state. So I have not described the details here. There are a lot of details here, but this is the main ingredient that or the main innovation of our work that I'm trying to present here. The rest of the work is very cleanly described in the appendix of our paper as well. So for the linearly connected oscillators, we also saw that the oracles that we constructed is efficient because you can see the circuit depth as well as gate count resources, which are not shown here. The resources kind of scale as a polynomial of log of n, which means polynomial of small n, and this is efficient. So we have all the ingredients that the exponential advantage requires. So we have these explicit oracles, we have the QSVT part, everything, and then so we have an end-to-end quantum algorithm that can potentially give a speed up if you run it on a fault-tolerant system. So now in implementation 3, what we did is we took the sparse state preparation of the first approach and the Oracle-based Hamiltonian simulation of the second approach, and we tried to kind of merge them to get an end-to-end implementation. And the reason why we did this was the main speed up in this algorithm was coming from the Hamiltonian simulation part. And we saw earlier that the sparse state preparation is efficient or at par efficient with the approach that is in the paper, at least for the linearly connected case. So merging this kind of made sense without losing this exponential advantage argument. And you can see the resources kind of reduced when we tried to use this implementation compared to the second implementation. And these are the simulation results on the classic platform. Detailed codes are available on the GitHub repo, which is open source, and you can see at the end of the slides. So thank you. I'll give the stage over to Dimitrios.
David, you're muted.
Sorry, I can't.
Oh, sorry.
David, you're muted.
Sorry, that's my fault. Before we move on, so there's one question. Among the 3 implementation methods tested, which one appears most promising for minimizing qubit requirements and circuit depth in real-world deployment?
Yeah, so that's a good question. So at least for the linearly connected case, I think the third implementation is very resource efficient, as well as we have tested it end to end to get the x of t and x dot of t results. So as of now, I can say the third implementation seems to be good.
Great. Thank you. So Dimitrios, you can keep going.
Sure, let me share my screen. All right, let me make it full screen. Okay, can you see my screen now?
Yes.
Perfect. All right, so yeah, first of all, let me very briefly thank the organizers for this very nice webinar, and also Ron and Viraj for setting up the ground for me. So essentially, I'm gonna just wrap up now the very nice presentation by Viraj by discussing the last of our main contributions, which is the applications. So now that Viraj has introduced the quantum algorithm, its implementations, the resource analysis, the different schemes that we applied to execute the algorithm, and also the benchmarking, the very next natural questions are, what can we do with it? So where can we apply it? What is this algorithm useful for? So here we wanted to ponder among these questions, and in our paper we also studied these 2 simple applications that I'm going to go through now. So the first one is the computation of normal modes. So normal modes are important for a physical system because it tells us its energy spectrum. It tells us the available energy states that the system can be. So now for this part of the presentation, I assume that this quantum state has been evolved according to the algorithm that Viraj presented. So once we have the final quantum state at some time t, we can apply this projector here to extract the kinetic energy. So this tells us the total kinetic energy of the linear chain of oscillators at some time t. Then we can repeat the same process of acting this projector at different time instances, and therefore we can create a function of time, kinetic energy as a function of time. Now, just for a mathematical convenience, we can subtract the total energy divided by 2, such that this function oscillates around 0 and not around some other numerical value. So this is just to remove a constant signal. And once we do that, we perform the discrete Fourier transform of this function to compute the kinetic energy as a function of frequency. So this gives us the kinetic energy in the frequency domain. The peaks of this function correspond to twice the normal modes. So omega alpha here is the normal modes, are the normal frequencies of the system. So just to summarize, with this projector, we can extract the kinetic energy, we compute this at different time instances, we do a Fourier transform, and we identify the peaks of this function. From the peaks, we can read the normal frequencies. Just to mention here, for comparison, classical methods actually scale exponentially with the size of the oscillators. So this is a very first proposal. If we have an exponential advantage evolved algorithm, what meaningful physical quantity we can extract. Now, furthermore, let me push this idea further and discuss some thermodynamics. Assume that we couple this linear chain of oscillators to some large reservoir of some temperature T. We can, define some useful thermodynamical quantities, in particular the partition function and the mean occupation number of its energy level. Again, this is the omega alpha are the normal frequencies. And from this, we can actually compute a bunch of important thermodynamical quantities, such the Helmholtz free energy, the internal energy, the entropy, and the heat capacity. Here are the definitions. I don't want to overwhelm you with equations. This does not matter. What matters is actually, if you see at the right-hand side of all of these equations, the only free parameter is actually omega alpha, which is the normal frequencies. So here you can see an example that once we extract the normal frequency from the system, we can actually do complete thermodynamics, which can be useful. For example, if we compute the heat capacity, we can know how fast this linear chain of oscillators can heat up or, cool down. Now, let me move on to the second application, modeling the wave equation. So first of all, the main idea is that we can split the linear chain of oscillators to different subregions. Each subregion has some number of oscillators, and then we can also apply again switchable projectors. So this projector extracts the first part of the column vector of the final state. So this gives us information about the kinetic energy, where this projector here can give us the potential energy. So, and then with these expectation values, we can compute the kinetic energy and the potential energy of each of these regions. So first of all, this is useful by itself. If for some reason you have a model, a physical system like a linear crystallic structure, and you want to keep track of the local energy, how it evolves in time, then you can just apply this switchable projectors on the appropriate part, and you can extract the total energy here, and you can keep track of time, how energy evolves in this region. However, we can do something more. So summing this, the kinetic and the potential energy, we have the total energy of its regions. And notice that, this is the wave equation. This tells us how energy propagates. It is useful to linearize this, not to linearize, but to discretize these derivatives. And this can be done by these formulas. The important thing is that, again, everything can be computed purely from the total energy that we know if we follow the protocol I just described. And if we take the square root of the ratio of these two quantities, we can compute the velocity, how energy flows from each of these regions. Now, if this quantities does not change in time and does not change from one region to the other, then that models exactly, the wave equation. All right, so let me just, conclude here with some final thoughts. So first of all, the main contribution of this work actually is that we provide a gap, if you want to, we provide a bridge to the gap between theory and implementation. In the literature, there is a lot of very nice works on the theoretical side. There are many nice works on the implementation side, but there are not so many bridging this gap. So this was actually our main motivation of this work, to study a concrete end-to-end realization of a very nice and promising algorithm, and try to provide the details such as oracle constructions that it's usually missing from the literature. Then we benchmark different strategies, as Viraj explained. We can use, for example, standard metrics that Classic provides, for example, circuit width, gate count, and all this, and we can use this actually to estimate the resources needed for each implementation, and therefore we can identify which implementation is the most optimal. And finally, we go beyond that, and we study, what physical systems such an algorithm can actually model, therefore, looking for a real world impact. So, to summarize these three lines, this work essentially is a concrete case study transforming a theoretical promising proposal to an executable algorithm that allows us also to go beyond just speculations, but also study, what interesting physics can be modeled there. However, there are some further interesting directions that one may wonder how better, what more can we do? And, the most natural extension is to go beyond the one-dimensional chain. This model, for simplicity, we study one-dimensional chain, but we can model more complex structures such as 2D or 3D oscillator networks. The crucial part is the scaling of the algorithm. So, as Viraj explained, so far, we find first evidence that this exponential speedup actually can be backed up by this executable implementation of ours. However, to truly claim an exponential advantage, one needs to scale this up to a sufficiently large number of oscillators. So this is a natural extension of this work, which of course is by no means is not trivial. And the final point is that it might be interesting, in connection also to the previous point, to develop a more hardware-focused implementation. So to adapt this circuit and these protocols of ours to a particular hardware, which will also allow us to account for the effect of noise. So here are the main references. So here is the link to the classic platform that Ron explained. This is the link to our GitHub repository, where we have all the codes for the implementation. And these are the two important references. This is the reference of the theoretical algorithm that we used, and this is actually the implementation. And with this, I would like to conclude, and thank you very much for your attention.
Great. Thank you, everybody. Thank you, everyone, for the presentations. So we're going to get into Q&A now. So one question is, how can coupled harmonic oscillator simulations on quantum computers help accelerate discoveries in material science, such as superconductors or next generation batteries? This is for, and everybody can answer, Ron, Dimitrios, Viraj.
Yeah, since I was speaking last on the application side, maybe I can take up first this question, and then we can continue with Viraj and the rest. So, of course, I think this will be a revolutionary point if one achieves it. Let me just comment that, as is usually it happens in physics and technology, we have to go step by step. So I think here there is not a paved pathway towards this to achieve this point, at the point of the question. However, the first practical need is to understand the properties of the mediums. In this work, we just described some of those properties. For example, you could see that how we can study the thermodynamics. So yeah, what I would say is that first of all, we need to understand the basic properties of the system. What is the energy spectrum, the available energy states of the system? This is what essentially we found from the normal frequencies. We can do thermodynamics. But then we need to add more complications, or more, to add more complexities to the formulation of the problem to see how much we can do with that.
Great, thanks. The next question is, what surprised your team most when moving from a theoretical correct algorithm to an actual end-to-end circuit implementation?
Yeah, I can go with this. From the first read of the paper, it seemed quite complicated to implement these things on a real platform. Because when you read papers, quantum algorithm papers that prove exponential advantage, you can see that the speed up argument is mostly in terms of Oracle complexity models, right? So in such cases, they don't provide explicit quantum circuits to do this. But from an implementation point of view, what we need is a quantum circuit that can give you the result that you want. So that translation itself from theory to practice is in general challenging if there is no explicit mentioning about the primitives used in the speed up arguments. Else, from an implementation point of view, once you know how to implement it, then you can use a classic platform which wonderfully builds these quantum circuits for you. So yeah, from the implementation point of view, there's no challenge as such, but translating that theory to implementation is a bit challenging in general.
Great, thanks. This one is for Ron. Does Classic plan to extend support for bosonic computers or alternative quantum simulators?
That's a great question. When currently the platform supports only gate-based simulations or computers, we do see, once we will see a concrete demand, I think we will definitely do it. So if this is a demand, so publish my email, I would be very happy to learn more about your users and deliver it to anyone relevant in Classic. And we would love to support if we see that it's something that is demanded. So yeah, why not? Not supported currently, unfortunately.
Great, thank you. One question, as quantum software stacks mature, do you believe the future competitive advantage will primarily come from novel algorithms, superior compilation synthesis techniques, or domain-specific optimization pipelines tailored to industrial problems?
So I would take this one. I would answer in a way that I believe that, as I saw when I was an application engineer working closely with our customers, like I was working with BMW as an example, and this is a good example. What I'm trying to say is that once you are getting very intimate with your problem, like you find a computationally hard problem, and you connect the lines between some background of some algorithms you heard about, and trying to see how these kind of algorithms can solve it, and going more and more intimate by coding, trying, validating, executing, thinking hard, publish an article, another article, and so on, and so increase the chances that you will find interesting solutions. So the reason I picked BMW, for example, is that when we worked with them on, I'm just sharing my screen, so you can see what they have done. So I was working with them in Munich, training them to see, this was already a trained team of quantum engineers, actually working on quantum for 3 years. And they say that in a workshop of 3 days, they implemented the most complicated algorithms they have ever done. So they did refer from another article that was already published about how you make optimization of electrical networks. They learned and understand this concept. And 1 year later, they developed this cooling system optimization notebook in one algorithm, combining 3 totally different algorithms, and QSVT with QAOA and quantum amplitude estimation in one application, one algorithm, connecting them all together. And their ability to do it was knowing very well the problem they are trying to solve, knowing the algorithms, and to bring innovation. So I think this is the way, of course, always after a lot of hard work and to summarize, this is everything. This needs research. You need tools, because here this was thanks to actually coding it and feeling in the hands what they are doing, catching the concept of what the algorithm is. It's very hard to learn, but thanks to programming it and actually doing it, you are able to understand it very well, executing, trying, publishing articles, building assets. That's what I think.
Great, thank you, Ron. Another good question is, do you see the future of industrial quantum computing being fully quantum or mainly hybrid systems where classical HPC and quantum processors work together? Anybody want to take that? Dimitrios, Viraj?
Yeah, I can go first. So I think, yeah, definitely it will be a mix of both classical and quantum computing. At least from the little experience that I have, I know that there are some good problems which you can solve by the mix of these two, especially in computational fluid dynamics. Not sure about this problem that we are working on, but I strongly believe that it's a mix of both.
Great, thanks. And Dimitrios, something to add or no? You're on mute.
Yeah, I think Viraj's answers covered it.
Great. Another question here is, what are the most reliable benchmarking matrices for comparing quantum algorithms across different hardware platforms?
Just a very quick comment on my end, at least. I think there are 2 very natural ones that people use in the literature, which is the gate count or if you want the circuit depth, and also the circuit width. So essentially the number of operators we need to apply to the system, and also how many qubits we need to model something.
Great, thanks. And that's a good one for industry. Which industries do you believe will first gain measurable commercial value from quantum simulations, like these energy, pharma, finance, or manufacturing? Anybody want to take that? Ron, maybe?
Honestly, I don't know. It's really hard to tell, because you see that all of the industries for sure are putting effort. They are trying hard to solve it. We see innovations in all different kind of industries. So it's really hard to predict if everyone is trying so hard. So one of them will soon make something interesting. I see someone, Vincent here, was answering finance, which is really interesting, because with small algorithms, you can make optimizations, and heuristic, maybe with machine learning, optimization, quantum Monte Carlo, and I'm not sure.
Great. We're almost wrapping up, so maybe one last question. Once fault-tolerant quantum hardware becomes available, how much faster or more accurate could these coupled oscillator simulations become compared to present-day implementations? Viraj, Dimitrios?
Yeah, I'm not sure what present-day implementation mean. I mean, I'm guessing that it would be the implementation that we have done. So yeah, so if we have a really good fault tolerant system, and you have seen the gate counts that is required to run this coupled oscillator problem, so then the algorithm that we have built is exact. Right, so the at least the first algorithm, the first implementation is exact. The second implementation might require some rounds of amplitude amplification to be done to get to the answer, and the third implementation is again exact. So if we have the fault tolerant device with all the specificities, like no errors in the gates, I mean having logical qubits and having all these number of gates, I think this should give an exponential advantage for large enough sizes.
I would also like to answer maybe something I didn't share that Classic is doing, and giving the answer exactly to, you don't see the right screen. So stop sharing and share. Okay. So another thing that Classic is doing, I did not present the layer that Classic is building for translating logical qubits into physical qubits. So it means that given an algorithm, we are building, what you see is all of the logical qubits and fault-tolerant operation of lattice surgery and magic peak cultivation that we are doing. We are using this tool at the end of the day to be able to take an algorithm and quantum error correction of our fault-tolerant implementation, the physical noise model of the hardware, that gives us the ability to give as an output the fidelity of how will this algorithm with this physical noise model will perform on a fault-tolerant quantum computer.
Great. Thank you, Rob. So wrapping this up, I'm just going to share my screen. So first and foremost, I'd like to thank everybody for joining today's webinar, and three other things, actually four other things. So one of them, we're going to have another webinar on June 11th. So keep an eye on our announcements. The second thing I'd like to mention is if you are a professional looking to learn more about what we're doing at Wiser, then you should look into our summer program. It's really an astonishing program that has been around for quite some time, and I really encourage everybody to register. The second thing is if you're in industry and looking to adopt quantum AI, HPCs through different ways of testing out, trying new ways of implementation of whatever industry you're in, then please do reach out to me. So my email is here, or you can add me on LinkedIn. And last but not least, if you're a startup with a great idea which is already scaling up and looking to have more visibility, of professionals test your platform, then you can also reach out to me, as we also have our insider programs. Thank you very much, everybody, for today. Thanks to the speakers, and thanks to all the great crowd with the great questions, and hope to see you at other coming events. Have a great rest of your day, evening, and see you soon.
Thank you very much, guys. Bye-bye.
See ya.
Thank you, David, for arranging this.
Thank you.